Hi, I'm Dr. Courtney. So we have a physics problem today about a parachutist jumping from a plane and accidentally dropping his cell phone. And be aware, I usually like to change the numbers a little bit so the student sees how the problem gets solved, but they need to solve it again themselves. So I like to begin with a picture. So the parachutist isn't the main issue here, but it's the cell phone. So we do have a parachutist kind of falling down here, and let's focus on the cell phone in his hand. And he drops his cell phone when he's at an altitude of 100 meters. And when he drops the cell phone, it has a velocity of 12 meters per second in the downward direction. So let's label this V initial is equal to negative 12 meters per second. And the negative helps us handle the fact that it's moving downward. And then it says, what is the velocity of the phone when it hits the ground? And a lot of students like to get cute here and they like to say, well, the velocity is 0 when it hits the ground. No, certainly a moment after it hits the ground, the velocity might be 0, but when a physics problem reads this way, it's really asking about the velocity the instant before it hits the ground. So what's going to happen here is that it says to neglect air resistance. Oh, we forgot to change the number. So rather than keep it 12 meters per second going down, so I don't end up solving it completely for the student, let's give it an initial velocity of negative 10 meters per second down, and then we'll ask about the final velocity and ignore air resistance. So we like to pause here. We like to say, well, what's the general principle of physics that's going to be used to solve this problem? And it's a projectile motion problem, or it's a falling object problem. So the general principle is really constant G. In other words, this is the idea going back to Galileo that G is equal to negative 9.81 meters per second squared. And in the absence of air resistance, all objects fall at the same rate. So there are different approaches here with the kinematic equations for the falling object. You could use the kinematic equations with the time. For example, there's an equation that says y final equals y initial plus v initial y times the time minus 1/2 gt squared. And there's also a kinematic equation saying v final equals v initial minus gt. And these are some common equations for projectile motion. But I also like to encourage students that if you have a problem where you're not given the time and you're not asked for the time, in that case you often want to use the kinematic equation without the time. V final squared equals v initial squared minus 2g delta y. And in this case, we have an initial velocity. We want to know the final velocity. And we have the delta y. It's 100 meters. And we have everything we need except for the final velocity, so we can solve for it. So let's go ahead and v final. Now, when you take the square root of both sides, you always need to be a little careful, because you always want to stop and ask, do I want the positive square root or do I want the negative square root? And in this case, as in a lot of physics problems, you want to appeal to your physical intuition. The cell phone is traveling downward when it hits the ground, so you want the negative square root. So it's negative the square root v initial squared minus 2g delta y. And you also need to take a little care when you're plugging in the numbers here that is the downward velocity going to be larger in magnitude when it hits the ground or smaller in magnitude? It's going to be larger in magnitude. So you need to take some care with the signs here. The delta y, let's just go ahead and plug in 10 meters per second squared minus 2 times 9.8 meters per second squared times 100 meters, but it's negative 100 meters because you start at a lower place than you begin. So the negative and the negative cancels out. So it's the square root of 100 meters squared per second squared plus, now 9.8 times 100 is 9,800 times 2, I think that's going to be 19,600 meters squared per second squared. So I'll leave plugging in the numbers and completing the algebra as an exercise for the diligent student so we can get along to the next problem. Okay, so the next problem says, on Earth, a ball is thrown straight downward with an initial speed of 1 meter per second from a height of 15 meters. And then what is the speed 0.6 seconds after it's released? So as usual, we want to draw a good picture. So the initial height is 15 meters. And the ball is thrown straight downward. And the initial speed is the initial speed is 1 meter per second, but we're going to make that negative because it's downward, and in our coordinate system we're going to have plus y being upward and plus x being to the right, so downward is negative. And so what's the speed of the ball 0.6 seconds after it's released? So we don't exactly know where it was, so at t equals 0.6 seconds, v final equals what? And I'm going to go ahead and I'm going to change this a little bit again so as to not deprive the students an opportunity to work it on their own. So I'm going to make the initial velocity, I'm going to change that to 2 meters per second rather than 1 meters per second. Now this is an example of a physics problem that gives a little extraneous information that you don't really need. In other words, as long as it's high enough to hit the ground, it doesn't really matter how high it is, because you're not asked for the speed when it hits the ground, you're only asked for the speed 0.6 seconds later. So you only need to be high enough that it doesn't hit the ground. You could be 100 meters high, you could be 200 meters high. We're ignoring wind resistance, doesn't matter how high you are. Okay, so in this case, we had the kinematic equation a little while ago. V final equals V initial minus there's no a half out there, that's another kinematic equation. V final equals V initial minus GT. V initial is the negative 2 meters per second, so V final equals negative 2 meters per second minus 9.8 meters per second squared, and now times the time, 0.6 seconds. So you plug in the numbers here and you'll have the final velocity, and if you notice that you could change what your initial velocity was, and that would change your final velocity accordingly. Okay, and once again we'll leave it as an exercise for the student to plug in the numbers to keep us on a good pace here, and we'll go ahead and have a look at the next one. Okay, so the next one says a girl throws a tennis ball upward with an initial velocity of 4 meters per second. What is the maximum displacement of the ball? Alright, so we'll have the ground here, we'll have our stick figure, and we'll have the girl throwing the ball upward. And in this case, V initial equals 4 meters per second. And we know intuitively what happens when we throw a ball up is the ball goes up. At some point, it reaches its peak of height, and then it turns around and starts coming back down. And a fact that you use in a lot of physics problems is that when a projectile, a ball, lots of different projectiles, is at the peak of its trajectory, its velocity is 0. So V final is 0 at the peak, because what we're interested in, intuitively we should know that the maximum displacement occurs when it's at its peak. So if we call the initial height of the ball, we'll let that be y equals 0. So what we want to know is we want to know y final when the final velocity is 0. And this is another circumstance where we're not given the time and we're not asked for the time. And while we could certainly solve two equations and find the time as an intermediate step, and I'll probably do it that way, but let me go ahead and demonstrate it with the kinematic equation without the time. We have V final squared equals V initial squared minus 2g delta y. And if you look at this, you realize there's no time in it. You have the initial velocity, you have the final velocity. G is just the acceleration of gravity, 9.8 meters per second squared, and delta y is that answer that you want. It's the maximum displacement. So in this case, you would solve it. Let's just do a little algebra here. V final squared minus V initial squared equals 2g delta y. Divide both sides by 2g. So here you get delta y equals V final squared minus V initial squared over 2g. And here you remember that V final is going to be 0. So, and you got a minus sign running around that might not make you comfortable, but really it's just whatever the magnitude of that is on the right hand side. Okay, so this is the way to work it, leaving the time out. The other way to work it is you use the equation V final equals V initial minus GT, and you can solve this equation to find the time. In other words, how much time does that ball spend going up? We're going to call that T up. So solving this equation, minus G T up equals V final minus V initial, and so minus G T up, V final is 0, equals minus 4 meters per second. So T up equals, negative signs cancel out, 4 meters per second over 9.8 meters per second squared. And when you look at the units carefully there, meters per second divided by meters per second squared is seconds. So I'll just leave it as 4 divided by 9.8 seconds for T up. And then you just have to find out how far up it went in that process by using the kinematic equation for the position. Y final equals Y initial plus V initial times the time minus 1/2 G T squared. We know Y initial is 0. V initial is your 4 meters per second. T up is whatever this fraction turns out to be. And G is the 9.8 meters per second squared. So I'll leave plugging in the numbers there as an exercise for the diligent student so we can get to the next one. Alright, so a pelican dives downward from a height of 35 meters with an acceleration of 9.8 meters per second squared to grab a sardine on the surface of the ocean. How long does the dive take? Alright, well, so there's the surface of the ocean. We have a height. I'm going to change the number here. I want to make the initial height, let's make it 40 meters. And the acceleration is 9.8 meters per second squared. And let's go ahead and let's put our coordinate system here where the sardine is. So this is y, this is x. So y initial is where the Pelican is starting its dive from, and then y final is the surface of the ocean. So that's 0. And so thinking about what we need to do here, which equation do we need? Well, we know that the initial height and the final height, and we have the acceleration, and we want to know the time. Now, the problem didn't really give us the initial velocity, but let's assume that the initial velocity is 0 meters per second, that the Pelican's kind of soaring along, maybe with a horizontal velocity, but with no vertical motion, sees the sardine, boom, goes and gets it. So the the vertical component of initial velocity, let's make that 0. So y initial equals y, y final equals y initial plus v initial times the time plus 1/2 at squared. And in this case, y final equals 0. Y initial is 40 meters. V initial is 0 because the Pelican isn't moving vertically. And then plus 1/2 A is negative 9.8 meters per second squared, and then times t squared. So a little bit of algebra here. 40 meters, negative 40 meters to the left-hand side equals minus 4.9 meters per second squared, t squared. And I just, 4.9 is 9.8 divided by 2. Cancel out the negative signs. T squared equals 40 meters divided by 4.9 meters per second squared. T is equal to the square root of 40 meters divided by 4.9 meters per second squared. All right, I'm having fun. I hope y'all are having fun out there too. I think this is the last one. We got one more to go. So I appreciate your patience and I appreciate you hanging with me out there. So the speed of a boat undergoing constant acceleration increases from 5 meters per second to 15 meters per second over a time period of 20 seconds. All right, so let's go ahead. Here's the surface of the water. This is a horizontal problem now. So we have a boat, not the best looking boat in the world, but you get the idea. So V initial is 5 meters per second. And then 20 seconds later, the boat's down here somewhere. V final equals 15 meters per second. And the time between these 2 points, let's call this t equals 0, and this is equal to t equals 20 seconds. And we want to know how far the boat traveled during that time. Now there's a couple of approaches here. We could use the kinematic equations, but it's actually harder to do it that way. If you think back to some of the things you may have learned before you learned about the vertical motion and the acceleration of gravity and the kinematic equations, one thing that you learned is that for constant acceleration, the average velocity is equal to the initial velocity plus the final velocity over 2. And then of course you know the distance, delta x, is going to be equal to the average velocity times the time. And what this approach allows us to do is it allows us to solve the problem more directly without computing the acceleration as an intermediate step. although maybe I should demonstrate it that way also. So doing it this way, the average velocity would be 5 meters per second plus 15 meters per second over 2, that's 10 meters per second. Delta x equals 10 meters per second times the 20 seconds, so that's the 200 meters. Alright, now let's suppose that we weren't that clever and we wanted to think about the acceleration and solve the acceleration as an intermediate step. As you recall from the definition of acceleration, by the definition of acceleration, it's the change in velocity, and these deltas that I like to throw around all over the place always mean the change. So it's the change in velocity over the change in time. So it's v final minus v initial over the change in time. So 15 minus 5 is 10 meters per second over the 20 seconds. So 10 meters per second divided by 20 seconds is 0.5 meters per second squared. And now x final, let's go ahead and call this x equals 0, and this is our x initial equals 0. X final's down here by where the boat ends up. X final equals x initial plus v initial times the time plus 1/2 at squared. So this would be 0 plus 5 meters per second times the time, and the time is 20 seconds, plus 1/2. The 1/2 comes from there, and then the acceleration is 0.5 meters per second squared, and then the time is 20 squared. So 5 times 20, this term here gives us 100 meters, and then 20 squared is 400, and then 400 times a half is 200, and then 200 times another half is another 100. So it was a little harder to work out that way, but we get the same answer. It was a pleasure working these physics problems for you today. Hoping you'll give me another chance real soon.